this week we met the notion of compactness, and as I have said, the notion of compactness is so different from open or closed. It's more abstract. As you can see, the definition of compactness is like so strange. For every open cover, there is a finite subcover, blah 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 blah. So I'll first explain why the definition looks like that, and I'll go through some basic properties or propositions. Definition. If I say, hey, and only if open cover, okay, there exists a finite subcover. Such that, let's see, right now. Okay. Alpha in A, U alpha. Alpha in A prime, U alpha prime, U alpha prime, where alpha prime is the subset of A and is finite. Such that it also covers K, so it also covers K.
Sorry, so what is K union of U alpha?
So what do you mean by open cover is a union of open sets that
Oh, I see.
contains.
So there's a comma after K.
Yeah.
Okay.
Sorry.
I see. So that is the unit of open set is the open line.
Let's say we have so many open sets here. Maybe infinitely many, but because the set is compact, so we can find it looks like a little bit messy, but we can find finite balls or finite open sets to cover this set. Why do we need this kind of notion? We're thinking about a question that as I said before, when we're talking about the topology of the set, we're talking about the behavior of the functions or the sequences of the set. So why do we need this kind of notions? Because that we want to make the continuous function bounded. So the purpose, or I'd say intuition of this is we want if f is compact set K, then f is numbered. So you're thinking that f is counted blah 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 blah. So what do we mean by this? We mean, I know we haven't talked about continuity, but I think we have meant this kind of notion in your calculus course. So just use that. O epsilon. This is delta. such as if x minus x prime is less than delta, then f of x prime minus f of x is less than epsilon. That's what we mean by continuous. So we're thinking that for every point, if you want to make it bounded, we're controlling like how large the function value varies in k, or at least for a point we control the value in this neighborhood. So like how do I draw? I'll draw it as a function r to r, something like this. As a function from a, b to r. And I'm thinking that for this point, there exists a delta here that controls the function between here and here. Is the graph clear enough? I'm not so sure. If you're controlling something like this, so you're doing this interval, and so you can control the function value in this interval. This one is delta, and this one is epsilon. So we fix epsilon, let's say equals 1. Then you have infinitely many open sets that that's the neighborhood that controls the value between 1. So given a point, let's say epsilon is 1, given this point, you can make, let's say, this interval so that this is 1. So you have, for every point, you can construct such a set. So you have uncountably infinite many sets. And you know that this set covers a, b interval. And if you know that it has finite subcover, which means that we only need finite these open balls, we can cover this set. And we know that in each open set, the function only vary, let's say 2 epsilon, so it varies of the value, the magnitude of 2. So let's say, okay, we know that there is only finite subcovers. So it looks like this one. We only need five open intervals, 5 open sets. And we know the functions here is maybe this f of a at epsilon between. We know that here is function value is between maybe here. And we know x0 is better. Sorry, x0. We know here is between fx1 minus epsilon f of x1 plus epsilon. We know here is blah 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 minus epsilon plus epsilon. So we can control the total difference of 2 epsilon times the number of intervals we need. so that the function is bounded. Is that cool for you? That's how I do compactness, like intuitively, but I'm not sure if you get.
So here the function is bounded, doesn't mean that the function won't go to infinity.
Yeah.
It's not different thing.
The function cannot go to infinity, it's the same thing. So let us say you have something, like maybe like 0, 1. This is not compact, so you can consider a function like this that goes to infinity. Or if the function is not bounded, then of course you can just maybe straight up to the side. But if the thing is bounded, then continuous implies the bounded.
Okay, so two things. The first thing is that under Rn, compactness is the same as closed and bounded. So if you think this is just completely bizarre, then by showing that a set is closed and bounded, you are actually getting compactness. But of course, if you go beyond Rn, then this equivalence will break down.
But this would
Yeah,
also,
but this definition is the weird, but yeah, but the universal definition.
yeah. So why do you think this is from, like, you are controlling the number of the open balls when you are manipulating these continuous definition. Okay.
I think that's one of the, okay, so, can you try to explain again the intuition, because it's still not clear to me. So you find all of, you fix an epsilon, and then for each point you find
A open interval.
I see, the delta, the open
Yeah, the
interval,
delta.
based on.
And because
the
that
delta, and then-
you only need finite subcover, so
I see,
in
okay.
each interval, the function varies little. And there are only finite open balls, so that you can.
So like
control
10,000 open balls. And
Yeah.
then, so at most, the f, the function can
Varies.
it can vary up to 10,000 epsilon.
Yeah, 10,000 times 2,000.
Yeah. But then.
Okay, so that's the intuition behind compactness. Of course, in this case, connected. It's not connected, it cannot be constrained this way. But this still holds. And you can control it in like another way, but I think that one. Actually, I historically it's not like this, but another proposition. But I think that this one's more straightforward.
I mean, historically, everything is backwards, right?
Historically, I believe that it's because of uniform convergence, but not this one.
Yeah, and I mean, if you think of it, Newton and Leibniz had no idea about epsilon delta. So.
Yep.
So,
That's what examples. Okay, first one is 0, 1 is not compact because you can consider let's say sorry, it should be n to the 1, 1 minus n to the 1, or not this one covers 0, 1. Right? So we're thinking about 0, 1. And the sets is like 1 over 3, 2 over 3, 1 over 4, 3 over 4. And it's growing, but they cannot meet this point. And if you only have finite open sets, then you end up with 1 over n, 1 minus n, 1 over n. And it does not cover 0, 1. And second, the finite sets are compact. And this one is straightforward because for every open cover, it's just for each point here, you pick an open set. Then you end up finite subcover. So that's, let's say we have, let's say 4 points. Let's say like this. And you can ask, okay, who covers you? And you'll say, okay, it covers me. Who covers you? Maybe you'll end up this covers me. Who covers you? You answer this. Covers this one. You may also answer this. So for every point, you just ask, okay, who covers you? Who covers you? Who covers you? You end up with finite open sets. So union them, you'll obtain a finite subcover. And for every open cover, you can operate the things that is. Cool. So, okay. So, how about empty sets? How about empty sets? Do you think, if you think empty set is compact, raise your hand. And if it's not, raise your hand. Why is compact? Anyone? Why is empty set open? Why is it compact? Okay. The reason why it is compact is because for every subcover, for adding open cover, you can pick a set, and the set contains the empty set. So that's the end of the story. Because every set contains empty set. So you just pick one set. Well, done. The story of empty set is a little boring, but you need to ask yourself about the whole space, the empty set, like this kind of thing, open so that you can make sure you understand those logical ambiguity. Maybe.
Wait, so basically any cover will cover an empty set.
Yeah.
So,
Yeah. So that you can just pick.
The empty set is.
Yeah.
That's cheating.
Yeah, that's cheating. So position So if something is not bounded, which means that you cannot cover that with a open ball, right? So you can consider something as a proof. Say S is not bounded. Take P in X. This one means the ambient state and ambient states. So X. And open balls. We use N, right? And MP for N. You know one thing that it covers S. But no subcover can do that because S is not bounded. But no tick for any finite subcover, M prime in, let's say, A and M from P. There exists a maximal in A. Let's say is A. And so R and M from P, the union, goes to NAP. It cannot cover S because S is not bounded. Can you read that? I don't think so. Because, no, not here.
Maybe you can put it on this side if you want.
Oh,
Below here, below that piece. That's why I like good notes.
the second compact closed. So let's say if it's not closed, then there is a limit point that is not contained in the set. So you can just push it to the limit point, but does not contain the limit point. So you imagine something like, let's say, here. You're doing something like, let's say, if you pick a point here, you're considering something here. This one's limit point. You don't want to touch this. Here you don't want to touch this. Okay, that's the intuition. The proof. As it's not closed, and some give me another, maybe Q is a limit point, but not in S. Consider open cover N 2 over D P Q P in S. They're doing like just cutting this halfway, so that it will not touch the limit point. Like for every, I'll not write it down. Make you have the feeling. For every finite subcover, you're constructing the minimum distance between your open cover and the limit point. And this distance will not be 0 because the set you take is finite. But it should be 0 because it is the limit point. So it cannot be compact. Done.
Can you explain again that graph?
I'll write it down. Sorry.
I mean, that graph, where is S?
Where is S? S is the set. We're trying to explain that S is not compact.
The graph.
The graph. The S is. This one is S. And this one is P. This one is N 2 over D P Q P. For every P, we construct this kind of interval. So it will not contain this one. You have a finite positive distance between your open cover and your point, and your limit point. But it should be 0 distance if the open cover covers the set, because it is the limit point. And any finite subcover cannot do that. Clear enough? I don't have to write it down.
Why the open cover needs to cover the limit point?
It does not need to out right now. Sorry. Consider this, like for all finite cover, let's say P from in S from and blah 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 blah. I have another. For all this kind of finite cover, then let's say here it says midpoint PQ, let's say R. The distance from R to P is controlled by, because you know R lies in here. So RP from plus DP from P. Sorry, it should be Q. RQ. RP from P from Q. It should be Q. So the distance between your point here and limit point is controlled by this one and this one. So sorry, it should be larger or equal to dp prime. This refers is reversed integration part dp prime q minus dr. Sorry, that should be correct. That one's good. So it's controlled by this one minus this one. The lowest is this one minus this one. Just move this here, and so dp from q is less than this two. Is that okay for you? So I'm saying this is less than, this one is controlled by this one minus this one. And you know, this one is at most, this is larger or equal, sorry, larger, it's less than. It's larger than dp from q minus 2 dp from q. So equals to dp from q. But you know this choice is finite here. So this number cannot be arbitrarily small. Right? So it should be larger or equal to d, let's say p at q, where p hat dp hat q equals to meaning dp from q for all, sorry, from in this one. So this is controlled by this one. Don't do the formula. Just imagine this graph and pick finite. So you have the nearest open interval to the limit point. But even is the nearest, there is a gap between the limit point and the interval, and it cannot contain the elements there. But in 2D, you're thinking about like, so this is a point, and you're thinking about like a set like this, open set like this. It cannot reach this point. So if you only have finite open cover, finite open sets, the nearest point to this one, it's not zero. The distance is not zero. So there exists some point is very near here that cannot be contained in this finite open cover.
So you're just saying that if the limit point is not in the set, then the open cover can cover everything.
Cannot.
Or if the limit point is not in the set, then only a infinite cover can cover the set. The finite cover would never.
If you design the this open cover in a very good way, so you always can think that a set have finite open cover that is the whole space itself, but it's not the definition. Our definition is for all open cover, you should exist a finite subcover. Now, I'm not saying that if it is finite, then it cannot cover. I'm saying that there exists a kind of open cover that cannot, we cannot find the finite open subcover.
So Tom, sorry, so you didn't write down what is R.
What is R? Oh, sorry. for pick and R in P from, in S from, and blah 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 blah. And P from
So in this subcover.
in this subcover, this point in this subcover, the distance to the new point is controlled. And its final notion about the contact in reverse proposition. If K, Y, X, then K compacts in X and compacts in Y. Before we do this, let's say, what do you mean by in X or in Y? We mean K is compact in this one, and K is compact in this one. So the distance between the 2 points are the same, or considering this and this. But the open sets, the shape of open set may not be the same because of the ambient space. Let's take an example. So what are the open sets? What are the open balls in, let's say, 0, 1 close interval? Open sets in 0, 1 close interval. Open balls. We're considering about balls. So maybe this one can be an open set in 0, 1 close interval. If you consider this one as ambient space, because you maybe say that, okay, 0, you cannot construct an open ball, but actually you can, because there's no elements here. We're considering about this. Your ambient set is 0, 1. All you care is elements in 0, 1. Okay.
So, sorry, I don't know where did I miss it, but what is ambient?
Oh, ambient means
Is it in the book?
it should be the whole space, the largest space, the space we're talking about.
Okay.
Like the ambient space. It's a nerdy way to talk about, or a mathematical way to talk about where we are talking, which space we're talking about. So we're talking about X. We're here. We're saying like, okay, now where the ambient space is X.
Okay.
This is not another meaning. We're just like saying that, okay, we're considering this set. Anything on this set.
So does that mean that I can say that, for example, if the ambient set X is R squared, then we just look at R.
Yeah, we just look at R. So you write down this one. This one is open in 0, 1. Is that okay for you? If this one is okay for you, then this is straightforward. because you just pick those open sub. If you have finite subcover here, and you pick the same open cover, finite subcover here. They prove sorry, here so here and prove this one. Cool. I forgot. I should talk about another proposition. That the closed subset of compact set is compact. Do you know how to prove it? Yeah, you should know. You should know how to prove it. I'll quickly explain that. So considering, that's proposition, I promise. Closed subset of compact sets is compact. So you consider proof. Consider let's say F, okay, this one's compact, this one's closed. Consider an open cover of F. Then U alpha union with FC. An open cover of K. Right? Because this one contains F, this one contains FC. These two combine is the whole set. The whole set, of course, covers K. And because K is compact, so you can find finite. So K is compact. Finite subcover. Let's say K from U alpha from. With or without this, it will be finite. So if you say, okay, this one is enough, and it's finite, we can add this one, like no matter what. So all right, this one. There exists this kind of finite subcover, and so you know that this have nothing to do with F. So you know F alpha U alpha prime contains F. So F has a finite subcover. Done. Okay, I think that's the end. You 要把它关掉吗？